Thank you for having me. Is it good? Loud enough? Everybody can hear? Okay, so thanks for having me. I'm working in Geneva on the Gaia mission, and I'm going to tell you about the story of us doing the science with Postgres. My story is a story of perpetual change if it comes to data handling. So I'm going to talk about, say a few things about this. Then I'm switching to database in astronomy. This is an interesting topic per se. And then I'm going to talk about Gaia mission, Gaia processing at Geneva and our data processing center. And Postgres for science, what does it mean for us? Then I'm going to speak about PostgreSQL, how we employed it, was it success or not, and collaboration with the Postgres community and the future. So I started quite early, my database career. I was at CERN for a few years, and it's important in the sense that I came to CERN as a neophyte believing in object-oriented databases. If you remember old days, 90s, there was a belief that object-oriented databases will take over the world. Well, they didn't, and the first thing I did at CERN was actually migration from object-oriented database into relational database. It resembles a little bit the story we've seen last years about MapReduce, NoSQL, and so on versus databases. And for the last 8 years, I'm part of the Gaia group in Geneva. So I started as data architect. Now I'm the leader and manager of the group. So at the time when I came to CERN, CERN was holding the biggest database in the world. It was 400 terabyte objectivity, object-oriented database. In fact, it was data store, page store in a sense. It wasn't really storing records, but objects as pages, distributing pages, file disk pages. At the time, it was quite popular, the ODMG Manifesto, Object Database Management Group, that was claiming that object orientation is the way to go. It will prevail. Relational databases are bound to fail and die. What was important, it was C++ binding for the physicists. The primary language at the time was C++. So C++ was the lingua franca in scientific community. It was quite fast, it was very expensive, and it was niche and stayed this way. In fact, I think disappeared in a sense now, so it's no more there. As I mentioned, object-oriented databases has been at the time what NoSQL has been recently, last years. It was handling certain things that were at the time thought as very important, like impedance mismatch, for example, the fact that the language, programming language is different than the data storage language. There was discussion what is better, graph versus relational. Most of this graph logic was implemented as so-called pointer swizzling. You had a pointer in memory in C++. If something was not in memory, you were basically swizzling the pointer, doing the fetch from the disk. And these two competing philosophies ended up, like a CERN case, that Oracle stepped in and offered their help. So, I have to change the word, sorry. So when Oracle stepped in, they asked us to do first rack installation, real application clusters installations. They offered C++ bindings. And in the end, we did the biggest migration at the time, not using RAG because it was not usable at the time. And at the same time, for me, it was an important point because I understood that probably relational databases are not that bad at all. They're actually quite good. They can perform. One of the reasons was SDSS. This is quite known in astronomical society. The survey, that is a ground-based survey, it's a relatively small telescope that is doing the survey of the sky. But part of this project, which was hosted in Baltimore, Hopkins University, was Jim Gray. If you're in databases, you probably heard the name. It was quite a person. He basically invented locking in databases. He was responsible for inventing 5-minute rule to what to store, what to cache in databases, and so on. And he was part of this project, and he kind of was part of this discussion, what is better, objectivity versus relational. He was part of Microsoft then, but I think I missed something. But the point is that he pushed for a relational model, and he showed that actually you can win with the relational model as a solution instead of the object-oriented database. So voila. So we have in astronomy, in principle, we see it changing, but for a long, long time, the primary format of the data was file. It was called FITS. It's a standard format. It's a container for image, basically, with some metadata. Then when the SDSS appeared, it was already quite big at the time. It was, at the end of the first iteration, it was 40 terabyte, plus 3 terabytes of processed data. And this internal competition was kind of turning point for the also astronomical or scientific society, because people who worked in, for example, SDSS moved to CERN as well. So I was working with one of them, and he said it was frustrating. He was also a believer in object-oriented databases, but in the end, he was converted to relational because of Jim Gray. He showed always, almost always, that you can do things better in a relational model, to frustration of some people, physicists, who believed in pointer Swizzling and so on. And now we have a lot of, 20 years later, we have a lot of astronomical projects that are basically defining the edge of the science because they are so big. All of these surveys are sensor data. You can hear about sensor data nowadays a lot because this is talk about Internet of Things, sensors everywhere. We carry sensors every day with us, so it's a deluge of data, flood of data. But in astronomy, Gaia is kind of the first such a big mission that is in space. Then there's a number of other coming. There's also ESA Euclid mission that is going to check for the dark matter. There's a James Webb Telescope, quite famous, mostly for money spent on it. It's huge. It's billions of dollars, tens of billions of dollars. It's going to be quite big, but not as big. But for space, it's still quite big. And then we have the ground-based, when this is the turning point. When you do things on the ground, you don't have to care too much about the downlink, which is quite a big limitation. So LSST, Large Sky Survey Telescope, is going to provide 60 petabyte, handle 60 petabyte of data with 15 petabyte as a result, as a final catalog. Then the things go crazy in next years, because then you have square kilometer array. This is radio astronomy, which will produce 300 to 500 petabytes per year. You can imagine this is 1 petabyte over 1 petabyte per day over many years. So 5 exabytes in total over many years. And then you have CTA, Cherenkov Telescope Array, which is basically looking for outbursts of the particles slashing the atmosphere particles. And this is going to be only 100 petabytes. But this shows you there's a lot of investigations in this community to how to handle this data. And the list goes on. And you can see here the sizes of the future sensors. So this is extremely large telescope, 30 meters, and this is Gaia. It's super small, and still we're delivering 1 petabyte of data as a consortium. So it's also important to mention that the environment changes. The astronomers started to understand years ago that new kind of models to handle the data are needed. And scientist becomes a data scientist, really. It's not scientist that deals with formulas. It's really dealing with the data. You have to look at the data. You have to know how to look at the data. You have to understand the structure. You have to understand the workflow. So you're basically becoming kind of computer scientist or data scientist. Is a kind of, it has to be like in both worlds. As a scientist, doing the domain knowledge, but also computing knowledge. And there's the role of a new SQL. I call it new SQL. It's not SQL because you have extended SQL. You have not purely relational model. There is good influences from object-oriented world that you should use. And of course, we know there is a lot of competition in this area. Recently, there's dozen or plus Apache projects that do other things like document stores. We have streaming frameworks. We have specialized hardware that can compress on the fly, and so on. And future is probably polyglot and hybrid stores. So we could probably merge all of them into one cohesive product. And it all depends on, of course, on your domain, on your project, on your requirements. But future is mixed. So it's good if you understand all of the pieces. Even if you know they are wrong in specific context, it's good to, even for discussion's sake, to know them. So one of our driving forces, if it comes to Gaia processing, is the fact to have unified, holistic view on the knowledge on the data. Again, from Jim Gray, he had this idea many, many years ago to have the one unified store for all the parts of the science. So not only the data, but also literature, but also methods, so software as a package that you show as a result of the science. So this is one of our goals as well in Gaia. And we're going to publish all the data. We do this in an iterative way. I'm explaining why. We cannot do this once. At the end of the mission, we're going to publish the whole code with Apache license, so open source, and also the methods. So we invent some methods specific to our processing. We're also going to publish this. So far, we had one data release, which was last year. From Geneva perspective, it was quite small, but it was first time over 1 billion sources was sources. When I say sources, I mean usually all stars or some astronomical objects that were published. And now we're facing data release 2, so actually it's going to be, for us internally, it's going to be next week. So sorry if the slides are not super prepared, because this is the reason. We're working hard on this. And the final data release will be in 2022. And everybody, you as well, feel invited to look at the data. There's a web archive. You can have a look, just Google it and you see it. So the ultimate goal is to create a catalog. And then you access this catalog, you will access this catalog through Gaia archive. And predecessor of Gaia, it was called Hipparcos. By the way, it was order of magnitude smaller. It provided 120,000 variable stars. We're going to provide probably 100 to 200 million. It was nicely published as a set of the books that you can put on the shelf. If we do the same for Gaia, in 2022, you'll end up with 10 kilometers of books. So of course, you cannot do this. You have to change your philosophy, how you access the data, how you publish the data. And let me tell you how Gaia mission is doing things. Why is it peculiar? Why is it so big? And so on. So what's so special about Gaia? First special thing is that it's a cornerstone mission. What does it mean? It means that for the next years or decades, it's not going to be similar mission. This is a big mission. I think if it comes to money, it's 50 million or 100 million euros plus. Gaia itself is around 1 billion over all these years from the inception till the end. And it's going to do census of the galaxy. So it's going to scan the whole sky every 6 months. And all objects between 6 and 20 magnitude in our galaxy will be recorded, and data about them, and stored and analyzed. So probably not everybody is aware what magnitude is. It's quite easy to convert to flux. In fact, the Gaia sees things in fluxes. Fluxes is electrons per second or photons per second. It's the same. And over 20 magnitude, you see 15, 20, less than 20 electrons or photons per second. So you can imagine how sensitive this tool is per star. We're going to gather proper motions, positions. Proper motion, I'm going to explain in a while what is this. Radial velocities, so how fast thing is coming to us or departing from us. And then we're going to see the spectrum. If you do a photo on your mobile phone or digital camera, you see the spectrum. So it's the same for here. For each observation, you will see the spectrum of this observation, some specific spectrum, not the whole spectrum. And we can also probably discover 10,000 exoplanets. Right now, I think it's around 6,000, 7,000, the total number of exoplanets discovered. And we believe, this was an assumption, but we see it's 15% more or less, population of all stars is variables. So this is what we're dealing with in Geneva. So a few words about the instrument itself. So Gaia, you see, this is the torus. These are two main mirrors. This is also quite a peculiar thing about Gaia. There are two mirrors, not one. And there is 1 gigapixel camera down there. There are a few other mirrors that basically capture the light from the main mirrors. And what's interesting also special about Gaia is that for the thermal stability, and this whole thing is made of the carbon. It's glued. It's actually monocrystal right now because it was baked, so there is no thermal kind of super stable thermally. Why? Because the angle between these two mirrors must be super stable. If it's not stable, we have to see how stable it is or unstable. And there's special interferometer that checks this angle that must be always the same. Why we need two mirrors? Because if you look one in the sky and then the other place in the sky, and you know the angle, then you can be sure that your accuracy is okay. If the angle is stable, of course. You're sure you're not making some small mistake. So you see the payload here. This is the sun shield, and this is the inside of the stand. You see the payload. One of the most expensive and difficult things to do is mirrors. Mirrors are quite special as well. There's a heating behind the mirrors, because every material that you have on the Earth is actually gathering some gas. It's degasified before the launch, but at some point this small particle of gas stay there and they start to evaporate and they make basically ice on the mirror. So few decontaminations were needed since the start in 2013, December. And right now it's the position of Gaia is Lassajou 2 point. There are few Lassajou points. One very nice point for the astronomers is the Lassajou 2. That means where this is the point where the gravitational forces of the Earth and the Sun are kind of equal. And Gaia is not a satellite per se, because it doesn't orbit Earth. It orbits with Earth, the Sun, like this. So it's never behind the Earth. It's never in the shadow of the Earth, but it's orbiting Sun. It's not orbiting Earth. And also the movement Gaia does is quite peculiar. It makes very strange kind of wobbling. So it is making this wobbling to see the sky, and this is these two places that it sees all the time, and making this small movement. The thrusters have power of the beam, more or less, to keep it so super accurate on its orbit. We can see it here. So this is view from inside. You will see how the light enters the spacecraft, and it's propagated, and how the scanning law, we call it scanning law, is working. It's important because this scanning law defines how much data we have per unit of time. Our unit of time, in a sense, here is half a year, because each half a year we scan the whole sky. So that means we do data reduction every half a year or every year, but we always work in the full sky kind of segments. So we have a number of segments that we work on. They are always covering the whole sky. Of course, there's a huge number of problems, technical problems that you have to deal, because the sensors is not perfect. As I said, I mentioned that you can have contamination of the mirrors, but you can also have some stray light. It was found out that this shield was cut, it's not properly, but it's normal that there are some fringes, and fringes cause the interference of the sun, and there's some sun entering the payload, even it shouldn't. So here you see how the scanning is done. And also, an interesting thing that Gaia already did is it's finding the proper motions of the stars, but in 3D. So thanks to this, you can see, here you can see the time that's passing. This is billions of years, right? So in billions of years, we see that, I don't know if it's visible, but some stars are moving, right? You see? And this particular star is coming to us in 1.5 billion years. It's going to be very close to Earth. It's 16,000 astronomical units, so quite close. Distances from the Earth to the Sun. So we could see that this was the closest point. But I think till then we're safe. And even then we should be safe if we're there. Okay, so Gaia processing in Geneva is what we do. I'm going to show how this whole consortium is set up. In the center we have ESA. This is placed in Spain. This is a quite big center, ESA center in Spain, where we have main database. In fact, this is not database, it's a set of files, because the internal format is files. They set up the infrastructure, so they impose certain things on us or all the other collaborators. Then we have Barcelona, which was responsible for simulations, for example. We have few groups. One main group is in Torino, DPCT. This is responsible for initial data look. And then we have, they are interconnected. Then we have Cambridge. Cambridge is important for us, for Geneva, because they deal with photometry. They actually see what things are good, what things are to be trashed. And then we got and they do calibration. This is super important. And when we got apparently calibrated data, we step in and we try to do variability studies. Variability studies are studies to look for variable stars. As I mentioned, 10–20% of the stars we assume are variable. The rest are constant. From our perspective, they are boring, because they don't change over time, at least for the human time, right? So this is where we are. There's also France, in Toulouse, quite big center where Ariane rockets are made, and there's a number of activities there. I'm showing this also to show that each of these groups uses different technology. So if it comes to databases, for example, ESA, the main center, uses either files, kind of hybrid solution, or intersystems cache. This is Hadoop, this is Oracle, this is Hadoop, and this is Hadoop. And we are Postgres. And there's also archive I mentioned that is accessible for everybody. And normally the whole consortium is around 600 people. 65 of those is in Geneva. You see our Geneva perspective is also quite distributed. We have collaborators all over Europe and Israel. So we have to deal with the scientists that want to see the data from many places in Europe. This is also a challenge. And scientific challenge is to classify things. So you have kind of taxonomy of the stars. I'm not going to go into details, but our task is to classify all the sources that we know nothing about but their photometry, how they change in time, how their luminosity changes in time, and to classify them in a specific manner. And thanks to this, we can do multiple things for physics, astrophysics, right? So this is important for not only for astronomy, but also for fundamental physics or astrophysics, because you can derive certain things about dark matter, or even distribution of the matter in the not only galaxy but also outside of galaxy, especially because we also see the quasars, which are super far away. And if it comes to the challenge of the volume, this is petabyte scale, but over the years. Right now we're finishing the DRC2, so data recycle 2, and it's around, for us, we are in red, so here the input data is around 100 terabytes right now. We might skip the next cycles, but at the end of the mission, we deal at each of the centers around with 1 petabyte of data. And then we have the challenge of the processing, so how to classify properly. So we have to do data import and transformation of photometry. I'm going to explain why. It's different than what we want. What we get is different what we really want to work on. Then we have data curation. You should never believe the data. Data is always wrong unless it's proven it's okay, because of human error, because of sensor error, because of the hardware error. And then we apply machine learning. We have to do sampling. We have to do batch processing. We have to do streaming. And then we have ad hoc analysis, which is basically analytics, right? And there we're trying to use this new SQL with Postgres and R and Java and multiple other languages that are suitable for specific tasks. Then we do data results curation, and then we export the data. And we have hundreds of Java classes. Java was, as I said, imposed in a sense on us, but it's okay. And then we have new SQL, and we have R, which is kind of prototyping platform as well. And then we have some kind of starting to play with memory-only solutions as well for certain smallest data sets. And all of this looks like this. It's quite typical flow. We get the data, we import some files every cycle. We're publishing these files to the database. There is in special formats, so we have to basically, you have our own parallel framework to ingest. Then we do reconstruction. I'm going to explain what time series reconstruction is. And then when we have a basic cluster of database cluster that we work on, then at all these stages, analytics could be done because we basically have everything in database. Also analytics, both scientific and technical. And then we process and then we export selected things via special format. So analytics are super important. We spend, I think, 80% of time on this. And this is where also Postgres is super important. So one of the discussion points between databases and NoSQL solutions or MapReduce is the data access. We know that we want very quick access to a single source. One of the 2 billion sources we want to have access millisecond. That is 3V velocity, variety, and volume problems. And we're dealing then with a hybrid kind of solution. But what is important that new SQL, so the SQL with some extensions, is our way to get super fast and kind of coherent access to the data. Also when the data is quite convoluted, and if they are convoluted in relationships between the data. So for this we're also using indexing techniques. And a very cool thing is sketches for the estimates and things like this. So this is example for the processing. The important part here is that to see that we limit the data as when we see it, but we see the gray boxes mean that we also have the manual kind of interaction with the data. So we see the need for people to interact with the data at all the stages. And this is also important not to believe in data. And then how Postgres fits into this picture. So I like this triangle because it shows you the freedom. I think all of us here like the freedom of choice, because this is why we're here with the free software. But this freedom of choice is kind of limited by a certain number of dimensions, or in dimensions. So one of them is tools. And these tools for us is Postgres. So we want open source, we want stable enough, and we know we want to scale well enough, because we cannot deal with 1 billion of whatever without scalability. And then why Postgres fits the picture. It's quite extensive. It covers indices, special indices that we need, spatial indices, for example, when we want to do some proximity searches of the stars. There's a number of indices, and we know we can write our own indices if you want. It has a number of languages supported, and it's extendable, so we can use extensions. And normally how the science looks like, we have some template configurations, we change this configuration, we're launching the workflow, and we repeat this. We have some results, we drill these results, we post-analyze these results after the big run. And this is run in the cluster of Geneva, for example, where we have more or less 1,000 cores to process, but these results must be exported to the people outside. So either we let them to access the system directly, or we export the Postgres as appliance. So this is another very cool feature, that you can export the whole stack as a virtual appliance, virtual host. And what we can do thanks to this, we can process a lot of data and export each subset of it to scientists to do their offline analysis. And of course, each iteration of like this is producing some results, so some volume that we produce is quite huge at some point, and we have freedom of choice to export what we want, analyze what we want. All our stack is running on Postgres, so we have also MetaMost, we have own cloud. We're very happy with this. And we also have our own dashboards that are being integrated with both MetaMost and own cloud for the sharing of the knowledge. Okay, we have also Kibana installed, so not only Postgres. And we also realized at some point that capturing soft knowledge is super important. So I would suggest that wherever you design your system, new system, you put kind of human-friendly parts of the model, so you can tag everything that it's supposed to change. You can put more soft knowledge as discussions, so you should capture discussions, annotations, both verbal and visual. We see that 90% of work, again, is computing. After computing is really discussions, is really analyzing of the data. So capturing this soft knowledge is super important in your model. So here, just example that you can annotate things visually and then store it in your model. And then we have the problem how to do this analytics. So we have a lot of things to deal with. We have hundreds of parameters and so on and so on. So we decided to use Postgres. I think obvious reason is that we need scalability. Postgres itself is not super scalable. Okay, you can scale vertically, so you can add more RAM, you can add more cores, you can add bigger machine, basically more disks. But at some point we realized that we need more, so we're thinking about implementing ourselves, but at the same time we noticed that there was PostgreSQL, which is the father of the PostgreSQL, which became a fork, because there's quite complicated story to this, but to put it to simple words, there was disagreement between how Excel and XC worked, or what is needed, and Excel was rewritten, was shared, kind of scattergather pattern was added. And thanks to this, we know that it's going to scale by architecture much better than XC, which doesn't have any specific pieces to scale up. It's just like kind of foreign data wrapper with sharding. So our perspective, we do this. So we give you that you may give. The old Latin sentence is really applying here, because we believe we can provide a test bed. We risk, of course, a lot, because we're agreeing to be a test bed for something that is not really finished. It's not super stable. At the time when we took over PostgreSQL and both XC and Excel, they were not super stable. But step by step, especially by big support from people from second quadrant, we were able to make it to work. And Gaia is extreme case for any platform. So this is a good example how you can employ a problem to elevate a system that you're using. Because, of course, if you have somebody to fix the problems. Because the problems that we're facing are not the problems everybody would face every day, because we have much bigger number of clients, sources, and so on. I mentioned we had one problem with the time series reconstruction. This is something related to how the data is gathered. So you see the 1 gigapixel camera. it's entering the star mappers, it's gathering, basically fetching the data. So Gaia is not sending images, it's really sending the time series data. But this time series data is not ordered in time. It's ordered by transits, and it's not ordered, sorry, by sources that they belong to. So there's a special process that assigns the transit that you've seen on the previous animation to the source. And then we have this for 10 to 9 sources, 1 billion, over 1 billion, 2 billion almost sources. Actually, it's 3 billion, but 1 billion is junk, so we say 2 billion. And we do distributed group by. This is what we really need. We want to order by time we want to group by source ID and order by time at the same time. So this is what we, in the end, from this, we want this. And this we got as a number of thousands of files in the special format. So we want to end up with this, which is a time series with some ordered time data. How we do this using PostgreSQL? So we have quite big table of these imported entities. This is more or less 30, 40 billion entries. We partition it, but we know when we partition a table in PostgreSQL, it's really distributed of a number of nodes. So currently we have 8 nodes. Each of the nodes holds part of the data. And thanks to this, we can quite easily do embarrassingly parallel processing on PostgreSQL, and we're getting huge speed up. Basically, what we were assessing years ago to take 2 or 3 weeks, we're doing in 12 hours right now. So it takes 12 hours to process 15 terabytes of data, to reorder it from one format to something that's usable for us when we can do actually our time domain analysis. And now we have 60 terabytes in live tables in database, and it's going to double every year. So real data, we have more, if you include backups and so on, but really usable data is 60 terabytes. And you see it's, okay, I'm not going to, of course, go into detail, but we have kind of poor parallelism in order to do this. The database is not that, or the planner is not that smart yet to do all the job for you, so you have to do some tricks, either refrain to processing on specific partitions, or even do directly things on the nodes. But the point is, we were able to do what we wanted in much better pace, in more comfortable situation. We could gain some time, we could add more iterations thanks to the speed we got from PostgreSQL. And this is so I'm not talking much about PostgreSQL, but in principle you have data nodes and you have coordinators. Here we see the kind of backup also solution when we shift the log from one machine to the other. This is in fact not in place because we had no time to deploy it simply, and it's also for us sometimes easier to redo the import. Each of the nodes has kind of quadruple role. It is primary storage, so it's primary coordinator and primary data node, and also backup, kind of shadow backup of the other nodes. So we have full symmetry. It's easy to buy, add new nodes. As long as they're symmetric, you can distribute your load and your data quite well. And what has been our involvement with PostgreSQL? We pushed patches, several patches, mostly related to scalability problems. We reported around 40 issues. Many of them were fixed. Thanks to this, we're actually in quite good shape nowadays. We still have few annoyances left. Some stuff should be fixed, some stuff should be added. We're waiting eagerly for Postgres 10, but we also created some extensions, so we can use extension to see the global views. There's no such a thing in PostgreSQL by default, but you can, using this extension, you can basically see the global activities from the whole cluster. You don't have to go node by node and see of them. You just see additional columns here specifying if it's what coordinator or data node it is. And in the future, we are super busy now with the data release, but we believe that PostgreSQL 10, that it's in works, has been in works for some time. We're super happy to see it's being synced more or less with the development of Postgres 10. It's going to be deployed. So we probably try to help to test version 10 as well, to stress and squeeze all the bugs out of it. And we want to be part of the Postgres 10 effort and Excel. And we're also going to expand the cluster. So in principle, we should get 14, 16 nodes at the end of the mission. We're expanding year by year. It's also very important because you can save money. It's important when you talk to your funding agencies. You don't have to buy a lot of hardware that's getting basically obsolete and that you have to pay much more because they retire much later. And I have to say that special thanks for Pavan and Thomas from Second Quadrant. They dedicated a lot of their time and effort in love to the project, PostgreSQL. So thanks again, and thanks for helping us and enabling us doing good science. Thank you.